Listening practice. Forward transportation engineering stands at the intersection of human ingenuity and societal progress. From the earliest footpaths carved by hunter-gatherers to the AI-driven smart cities of today, the evolution of transportation systems has mirrored humanity's quest for connectivity, efficiency, and equity. Ancient civilizations laid the groundwork with innovations like the Roman road network and the Silk Road, which fused trade with cultural exchange. The Industrial Revolution propelled us into an era of steam engines and automobiles, redefining mobility but also introducing challenges like urban sprawl and fossil fuel dependency. Today, we face a pivotal moment. Climate change, population growth, and technological disruption demand reimagining transportation as a force for sustainability and social justice. This book emerges in an era where transportation is no longer just about moving people and goods, it is about reshaping cities, conserving ecosystems, and bridging divides. Congestion chokes megacities, emitting greenhouse gases and eroding quality of life. Marginalized communities disproportionately bear the brunt of pollution and inadequate transit access. Meanwhile, breakthroughs in autonomous vehicles, renewable energy, and data-driven systems offer unprecedented opportunities to design equitable, resilient networks. Modern transportation engineering does not merely chronicle these challenges, it equips readers to solve them. By blending historical context with cutting-edge innovation, this text underscores transportation's role as both a catalyst for progress and a mirror reflecting societal values. As you turn these pages, consider how every road, rail line, and algorithm can be a step toward a world where mobility is safe, sustainable, and inclusive. Preface. Transportation engineering is a dynamic field where tradition meets transformation. This book bridges the gap between foundational principles and tomorrow's technologies, offering a roadmap for professionals and students alike to navigate the complexities of modern mobility. Scope and objectives. This comprehensive guide is structured to serve as both a textbook and a practical manual. It begins with the fundamentals of transportation systems planning, traffic theory, and infrastructure design before advancing to specialized topics like intelligent transportation systems, ITS, sustainable urban mobility, and emerging technologies such as autonomous vehicles and 3D printed infrastructure. Each chapter integrates theory, core concepts in traffic flow, geometric design, and materials science. Practice, real-world case studies, e.g., Copenhagen's cycling revolution, Japan's Shinkansen. Innovation, breakthroughs in green infrastructure, AI-driven logistics, and climate resilience. A unique emphasis is placed on sustainability and equity, reflecting the urgent need to decarbonize transport while ensuring access for all communities. Target audience. This book is designed for engineers and planners, professionals seeking to integrate smart technologies and sustainable practices into projects. Policymakers, leaders crafting regulations to balance economic growth with environmental stewardship. Students, graduate and undergraduate learners in civil engineering, urban planning, and environmental science. Researchers, innovators exploring frontiers like vehicle-to-grid integration or bio-based pavement materials. Pedagogical features, case studies, lessons from iconic projects, e.g., Panama Canal expansion, Dubai's autonomous transit. Design examples, blueprints for intersections, EV charging networks, and flood-resilient roads. Discussion questions, critical thinking prompts linking theory to ethical and practical dilemmas. Appendices, quick reference tools, including formulas, compliance checklists, and sample designs. A vision for the future. Transportation is more than steel and asphalt, it is the lifeblood of economies and the fabric of communities. This book challenges readers to envision systems that prioritize people and planet, leveraging technology not for its own sake, but to create a world where mobility empowers rather than excludes. Whether you are designing a bike lane or drafting a national freight policy, the principles within these pages will guide you toward solutions that endure. Let me know if you'd like to refine or expand any section further. Part I, Fundamentals of Transportation Systems 1. Introduction to Transportation Engineering 1.1 Historical Development and Global Impact, Ancient Innovations, Early Footpaths, Animal-Drawn Vehicles, and River Navigation. Roman Engineering Marvels, e.g., Appian Way, and their role in military and trade expansion. Medieval Trade Networks, Silk Road, Hanseatic League. Industrial Revolution, Steam Engines, Railroads, e.g., Liverpool and Manchester Railway, and the birth of mass transit. Automobiles, Ford Model T, and highways, reshaping urban landscapes. Modern Era, Air Travel, Wright Brothers, Jet Age, and Globalization. Digital Revolution, GPS, Smart Mobility, and Hyperloop concepts. Global Impact, Economic growth via interconnected supply chains and trade corridors. Urbanization and suburban sprawl, e.g., post-World War II U.S. highway expansion. Cultural exchange and geopolitical influence, e.g., Panama Canal's strategic role. 1.2 Modes of transportation, road, rail, air, water, and pipeline, road transport, flexibility and dominance in last-mile connectivity. Challenges, traffic congestion, e.g., Los Angeles, Mumbai, maintenance costs. Rail transport, high-capacity freight and passenger systems, e.g., Shinkansen, Trans-Siberian Railway. Energy efficiency versus high infrastructure investment. Air transport, speed and global reach, e.g., Dubai International Airport. Environmental footprint, 2.5% of global CO emissions. Water transport, cost-effective bulk shipping, e.g., Suez Canal, container ships. Limitations, slow speed, port congestion. Pipeline networks, safe transport of oil, gas, and water, e.g., Keystone Pipeline. Risks, leaks, geopolitical tensions. 1.3 Key challenges, congestion, safety and environmental degradation. Congestion, causes, urbanization, induced demand, inadequate public transit. Economic toll, $305 billion annual loss in the U.S., 2021. Solutions, congestion pricing, e.g., London, integrated urban planning. Safety, global road fatalities, 1.3 million annually, with vulnerable users, pedestrians, cyclists, at risk. Innovations, autonomous emergency braking, Vision Zero initiatives. Environmental degradation, emissions, transport contributes 24% of global CO, IEA, 2023. Mitigation, electric vehicles, EVs, green fuels, and circular economy practices. Ecological impact, habitat fragmentation, e.g., Amazon Road Network. Key themes, interconnectedness, how historical advancements shape modern challenges. Sustainability, balancing efficiency with ecological and social equity, e.g., EV adoption in Norway. Innovation, emerging technologies, e.g., AI in traffic management, as solutions. Case studies, congestion, Jakarta's Trans-Jakarta BRT system reducing traffic by 30%. Safety, Sweden's Vision Zero reducing fatalities by 50% since 1997. Environment, the Netherlands cycling infrastructure cutting emissions. Discussion questions. 1. How might ancient transportation networks inform modern sustainable design? 2. Which mode offers the best balance of efficiency and environmental impact? 3. Can technology alone solve congestion, or is behavioral change essential? This chapter lays the groundwork for understanding transportation's evolution, diversity, and pressing issues, setting the stage for deeper exploration in subsequent sections. Chapter 2, Transportation Planning and Policy 2.1 Urban and Regional Planning Frameworks Overview. Urban and regional planning frameworks integrate transportation systems with land use, economic growth, and community needs. These frameworks ensure cohesive development while addressing challenges like population growth, equity, and technological disruption. Key concepts: land use integration, aligning transit networks with zoning laws to promote mixed-use development, e.g., transit-oriented development, TOD. 4-step model, one-trip generation, estimating travel demand based on demographics. 2-trip distribution, mapping origins and destinations. 3-mode choice, predicting preferences, car, transit, cycling. 4-route assignment, allocating trips to infrastructure. Regional coordination, cross-jurisdictional collaboration for highways, rail, and air corridors, e.g., EU's Trans-European Transport Network. Case studies: Singapore, integrated land use and transit planning reduced car dependency, 12% car ownership. Copenhagen, prioritized cycling infrastructure, 45% commuters bike daily. Challenges: balancing stakeholder interests, e.g., developers versus environmentalists. Adapting to autonomous vehicles and ride-sharing disruptions. 2.2 Environmental and Social Impact Assessments ** Overview, mandatory evaluations to minimize ecological harm and ensure social equity in transportation projects. Key concepts: Environmental Impact Assessment, EIA, air/noise pollution, mitigation via electric buses, e.g., Shenzhen's all-electric fleet, habitat protection, wildlife corridors in highway design, e.g., Banff National Park, social impact assessment, SIA, equity, ensuring access for low-income and disabled populations. Community engagement, participatory planning to prevent displacement, e.g., Atlanta Beltline. Regulatory context, NEPA, U.S. requires federal projects to assess alternatives and impacts, EU EIA directive, mandates public consultation and climate considerations. Case studies: Dakota Access Pipeline, controversy over tribal lands and water safety. California High-Speed Rail, delays due to land acquisition disputes. Mitigation strategies, green infrastructure, e.g., permeable pavements. Noise barriers and community benefit agreements. 2.3 Funding models and public-private partnerships, PPPs, overview, financing mechanisms to address infrastructure gaps amid rising costs and climate priorities. Key concepts: traditional funding, fuel taxes, tolls, e.g., U.S. Highway Trust Fund. Municipal bonds, e.g., New York MTA's $51 billion capital plan. PPPs, design build finance operate, DBFO private sector manages projects for long-term revenue, e.g., Indiana toll road lease, risks, cost overruns, e.g., London Underground PPP collapse, innovative models, value capture, taxing property value gains near transit hubs, e.g., Hong Kong MTR, green bonds, funding sustainable projects, e.g., Dutch A6 highway. Case studies: Denver Eagle P3, successful PPP expanding regional rail. Singapore's congestion pricing, reduced traffic by 20% during peak hours. Challenges: ensuring transparency and equitable access in PPPs, adapting to post-pandemic revenue shortfalls, e.g., transit ridership drops. Discussion questions: 1. How can TOD frameworks address urban sprawl in fast-growing cities? 2. Should EIAs prioritize climate resilience over cost efficiency? 3. Are PPPs viable for low-income regions with limited private interest? Emerging trends: COVID-19 impact, shift to remote work altering transit demand. Digital tools, AI optimizing toll pricing and equity assessments. This chapter equips readers to navigate the complexities of planning, impact mitigation, and financing, emphasizing sustainability and equity in modern transportation systems. Chapter 3, Traffic Flow Theory and Analysis 3.1 Macroscopic versus Microscopic Traffic Models Overview. Traffic models simulate how vehicles move through networks, guiding infrastructure design and management. Two primary approaches are used: macroscopic models, definition, treat traffic as a continuous flow, analogous to fluid dynamics. Key variables: flow, q vehicles per hour, v/hr. Density, k vehicles per kilometer, v/km. Speed, v kilometers per hour, km/hr. Fundamental equation, q equals k times v . Applications, highway capacity planning. Traffic signal timing optimization. Tools, Highway Capacity Manual, HCM, for U.S. standards. Software, Transit for signal coordination. Microscopic models, definition, simulate individual vehicle behavior, including driver decisions. Key concepts, car following models, rules for acceleration/braking, e.g., Gibbs model. Lane changing logic, simulates merging and overtaking. Applications, evaluating autonomous vehicle interactions. Testing new intersection designs. Tools, software, Vissim, Sumo. Comparison, macroscopic, efficient for large-scale networks but lacks granularity. Microscopic, high detail but computationally intensive. 3.2 Queuing Theory and Capacity Analysis Overview. Queuing theory analyzes delays and bottlenecks, while capacity analysis determines maximum sustainable traffic flow. Key concepts, queuing metrics, arrival rate, lambda vehicles arriving per unit time. Service rate, mu vehicles processed per unit time. Queue length, L equals frac lambda 2 mu, lambda, 4m/m/1 queues. Capacity analysis, critical density, maximum vehicles per km before congestion. Highway Capacity Manual, HCM defines capacity for roads, e.g., 2200 v/hr/lane for freeways. Applications, toll plazas, optimizing booth numbers to minimize wait times. Traffic signals, balancing green time for peak flows. Case study, Los Angeles I-405 expansion, used queuing theory to predict post-construction congestion reduction, actual results mixed due to induced demand. 3.3 Level of Service, LOS, and Performance Metrics Overview. LOS grades traffic conditions, AF, based on user experience, while performance metrics quantify system efficiency. Level of Service, LOS, criteria, A, free flow, minimal delays. F, gridlock, unpredictable delays. Determination, highways, based on density, e.g., less than or equal to 7 v/km/lane for LOS A. Intersections, delay per vehicle, e.g., less than or equal to 10 sec/v for LOS A. Criticisms, favors car throughput over pedestrians/bikes. Cities like Los Angeles are shifting to multimodal LOS, UMLOS. Performance metrics, travel time reliability, percentage of trips within expected duration. Delay, extra time due to congestion, e.g., 42 hours/year per U.S. commuter. Environmental impact, CO emissions per vehicle mile. Emerging trends, vulnerable user LOS, prioritizing safety for cyclists/pedestrians, e.g., Seattle's road safety dashboard. AI-driven metrics, real-time congestion prediction using machine learning. Discussion questions. 1. When would a planner choose macroscopic over microscopic models? 2. How does induced demand challenge traditional capacity analysis? 3. Should LOS prioritize equity, e.g., bus riders, over car throughput? Key takeaways, integration, combine macro/micro models for holistic planning. Innovation, machine learning and UMLOS address modern urban challenges. Equity, metrics must reflect diverse user needs in sustainable cities. This chapter equips readers to analyze traffic systems critically, balancing efficiency, safety, and inclusivity. Part 2, Transportation Infrastructure Design. Chapter 4, Highway Geometric Design. Highway geometric design focuses on creating safe, efficient, and sustainable roadways by optimizing physical layout and alignment. This chapter covers critical principles, standards, and modern practices in highway design. 4.1 Alignment, cross-sections, and sight distance. Key concepts: alignment, horizontal alignment, curves, super elevation, banking, and transition spirals to balance speed and safety. Minimum radius formula, /r_text min equals \frac v2 127, e plus f, where v equals design speed, km/h, e equals super elevation, f equals side friction factor. Vertical alignment, grades, crest curves, sag and crest vertical curves, to ensure visibility and drainage. Cross sections, lane width, typically 3.6–3.7 m for highways, narrower lanes in urban areas, 2.7–3.3 m. Shoulders, 2.4–3.0 m for emergency stops, paved or stabilized materials. Medians, 4.8–15 m for divided highways, may include barriers or green spaces. Drainage, crown slope, 2–3%, and side ditches to prevent water accumulation. Sight distance, stopping sight distance, SSD equals VT plus \frac V2 254, F \PMG, where T equals reaction time, 2.5 SEC, G equals grade. Passing sight distance, PSD critical for 2-lane highways, 405–50 m. Decision sight distance, extended visibility for complex maneuvers, e.g., interchanges. Applications, mountain highways, tight curves with guardrails and runaway truck ramps, e.g., Colorado's I-70. Urban arterials, narrower lanes with bike lanes and curb extensions, e.g., Amsterdam's Woonerf zones. Case study, I-95 reconstruction, USA improved vertical alignment to reduce flooding risks in coastal regions. Challenges, balancing terrain constraints, e.g., Himalayas, with safety standards. Retrofitting aging infrastructure for modern vehicle dynamics, e.g., EVs, autonomous trucks. 4.2 Intersection design, roundabouts, signalized, and unsignalized. Key concepts, roundabouts, design elements, inscribed diameter, 3100 m, entry/exit angles, and splitter islands. Benefits, 35–50% fewer crashes than signalized intersections, lower emissions. Standards, yield at entry, pedestrian crosswalks 5–10 m back. Signalized intersections, phasing, optimized cycle lengths, 6120 SEC, and green splits using software, e.g., Synchro. Left turn treatments, protected/permitted phases, dual left turn lanes. Unsignalized intersections, stop/yield control, two-way stop, TWSC, or all-way stop, AWSC, based on traffic volume. Priority rules, major road dominance, gap acceptance models for minor road entry. Applications, Carmel, Indiana, USA 140 plus roundabouts reducing injury crashes by 80%. Adaptive signals, Los Angeles AI adjusts timing in real time during peak hours. Case study, Shibuya Crossing, Tokyo high-capacity signalized intersection handling 3,000 plus pedestrians per green phase. Challenges, designing for multimodal users, e.g., cyclists in Dutch roundabouts. Retrofitting signalized intersections for CAVs, connected and autonomous vehicles. 4.3 Design Standards, OSHTO, MUCT, Key Standards, OSHTO Green Book, Design Speed, dictates geometric parameters, e.g., curve radius, sight distance. Context classification, rural versus urban, freeway versus arterial. MUCT, Manual on Uniform Traffic Control Devices, Signage, retroreflective materials, size, and placement, e.g., stop signs at 750 mm, pavement markings, thermoplastic or epoxy for durability, e.g., 150 mm lane lines, signal heads, LED technology for visibility and energy efficiency. Global variations, EU, and 12,899 reflective signage standards for trans-European road networks. India, IRC 67 adaptations for mixed traffic, e.g., bullock carts, rickshaws. Case study, Autobahn, Germany. No general speed limit but strict geometric standards, e.g., 4.0 m lanes, 250 m SSD. Challenges, harmonizing standards for cross-border corridors, e.g., ASEAN highway network. Updating MUCT for emerging technologies, e.g., digital signage, V2X communication. Discussion questions. 1. How does super-elevation improve safety on curved highways, and what are its limits? 2. Should roundabouts replace all signalized intersections in urban areas? 3. Can OSHTO standards accommodate hyperloop or flying vehicle infrastructure? Emerging trends, green geometric design, permeable pavements, bioswales in medians. Autonomous vehicle readiness, wider lanes for sensor margins, dedicated CAV lanes. Key takeaways, safety first, sight distance and alignment are non-negotiable for crash reduction. Flexibility, standards must evolve with climate change and technological disruption. Equity, prioritize vulnerable users, e.g., ADA-compliant ramps, pedestrian refuges. This chapter provides the blueprint for designing highways that balance safety, efficiency, and sustainability in a rapidly changing world. Chapter 5, Pavement Engineering. Pavement engineering is critical for designing durable, cost-effective roadways that withstand traffic loads and environmental stressors. This chapter explores material choices, life cycle management, and strategies to extend pavement longevity. 5.1 Flexible versus rigid pavements, materials and design life. Flexible pavements, materials, surface layer, asphalt, concrete, bitumen and aggregates. Base/subbase, crushed stone, gravel, or recycled materials. Design life, 15-20 years, shorter under heavy traffic or extreme climates. Advantages, smooth ride quality, easier and faster repairs. Cost-effective for low to moderate traffic volumes. Challenges, susceptible to rutting, cracking, and temperature sensitivity, e.g., softening in heat. Rigid pavements, materials, slab, Portland cement concrete, PCC, with steel reinforcement. Subbase, stabilized soil or lean concrete. Design life, 20-40 years, longer lifespan but higher upfront cost. Advantages, high load-bearing capacity, ideal for airports and heavy freight corridors. Resistant to oil and fuel spills. Challenges, joint maintenance, reflective cracking over time. Comparison table, factor flexible rigid initial cost lower higher maintenance frequency frequent infrequent climate suitability moderate, avoid extreme heat, all climates traffic adaptability low to medium high. Case study, I-35W, Minnesota hybrid design using rigid pavements for truck lanes and flexible for general traffic. 5.2 Pavement Management Systems, PMS, components, data collection, surveys, laser profilers, drones, and ground-penetrating radar, GPR. Sensors, IoT devices for real-time monitoring of moisture and stress. Condition assessment, Pavement Condition Index, PCI rates distress, e.g., cracking, potholes, on a 0-100 scale, remaining service life, RSL predicts lifespan using machine learning. Decision-making, prioritizes projects via cost-benefit analysis, e.g., HDM4 software. Benefits, reduces life cycle costs by 20-30% through proactive planning. Enhances safety by addressing critical defects early. Case study, Caltrans PMS, integrated GIS and AI to optimize $5 billion annual maintenance budget. Emerging trends, digital twins, virtual models simulate climate and traffic impacts. Blockchain, tracks material provenance and maintenance history. 5.3 Rehabilitation and maintenance strategies. Maintenance, preventive, flexible, crack sealing, chip seals, fog coats. Rigid, joint resealing, dowel bar retrofits. Corrective, pothole patching, slab replacements. Rehabilitation, flexible pavements, overlays, hot mix asphalt, HMA, or cold in-place recycling, CIR. Full depth reclamation, FDR recycles existing layers into new base material. Rigid pavements, diamond grinding, restores smoothness and skid resistance. Ultra-thin white topping, concrete overlay on asphalt. Innovations, self-healing asphalt, microcapsules release bitumen to fill cracks. Geosynthetics, reinforce weak subgrades and reduce reflective cracking. Challenges, balancing traffic disruption with repair quality, e.g., nighttime work in urban areas. Funding constraints for long-term sustainability, e.g., carbon tax incentives. Discussion questions. 1. Can recycled plastics replace bitumen in flexible pavements without compromising durability? 2. How might climate change alter pavement material selection by 2050? 3. Should governments prioritize rigid pavements for freight corridors despite higher costs? Key takeaways: sustainability, recycled materials, e.g., tire rubber, plastic waste, reduce environmental impact. Technology, AI and IoT transform PMS from reactive to predictive. Equity, rural versus urban funding allocation for maintenance. This chapter equips engineers to design, manage, and rehabilitate pavements that meet evolving demands for resilience, efficiency, and sustainability. Chapter 6, Public Transit Systems. Public transit systems are the backbone of sustainable urban mobility, reducing congestion and emissions while enhancing accessibility. This chapter explores key modes, design principles, and integrated development strategies. 6.1 Bus Rapid Transit, BRT, and Light Rail Transit, LRT, definitions and features. BRT, infrastructure, dedicated lanes, elevated stations, off-board fare collection. Vehicles, high-capacity buses, e.g., bi-articulated, electric. Examples: Bogotá's Transmilenio, 113 stations, 2.4 million daily riders. Istanbul Metrobus, 52 kilometers dedicated lanes, 800,000 passengers/day. LRT, infrastructure, rail tracks, street-level or elevated lines. Vehicles, electric trams or light rail cars, e.g., Siemens Avenue. Examples: Portland Max, 97 km network, integrates with buses/bikes. Melbourne Tram Network, largest globally, 250 km of track. Comparison, factor BRT LRT cost lower, $5 $20 m/km, higher, $20 100 m/km, capacity 10,00035,000 pax/hr/direction 8,00025,000 pax/hr/direction. Environmental impact: hybrid/electric options reduce emissions, zero tailpipe emissions, electric, flexibility, adaptable routes, fixed infrastructure. Challenges: BRT, mixed traffic bottlenecks, perception as second-tier transit. LRT, high upfront costs, construction disruptions. Case study: Curitiba BRT, Brazil pioneered BRT in 1974, inspired global systems. 6.2 Rail network design and scheduling. Design principles: network topology, hub and spoke, central hubs, e.g., London Underground. Grid, decentralized connectivity, e.g., New York Subway. Station spacing, urban, 0.51 km, e.g., Paris Metro. Suburban, 25 km, e.g., Berlin S-Bahn. Scheduling strategies, peak frequency, 25 min headways, e.g., Tokyo's Yamanote Line. Off-peak, 10-15 min headways. Tools, automated train control, ATC ensures safety and precision. Real-time apps, City Mapper, Transit. Case study, Tokyo Rail, 158 lines, 95% on-time rate via AI-driven scheduling. Challenges, balancing capacity with demand fluctuations. Aging infrastructure, e.g., NYC's 100-year-old signals. 6.3 Transit-Oriented Development, TOD, Principles, Mixed-Use Zoning, Residential, Commercial, and Recreational Spaces within 800 m of transit. Density, 5150 units/acre near stations. Walkability, pedestrian plazas, shaded sidewalks, bike parking. Benefits, ridership boost, Arlington, VA's Rosslyn-Ballston corridor increased metro use by 40%. Economic growth, Hong Kong MTR profits from property development. Challenges, gentrification, displacement of low-income residents, e.g., San Francisco's Mission District. Zoning barriers, parking minimums, height restrictions. Case study, Singapore's Jurong Lake District, TOD with 100,000 homes, 20,000 jobs near MRT stations. Emerging trends, green TOD, solar canopies, rain gardens at transit hubs. Equity tools, inclusionary zoning for affordable housing. Discussion questions, 1. Can BRT rival LRT in prestige and ridership with sufficient investment? 2. How might autonomous buses reshape traditional rail network planning? 3. Does TOD exacerbate inequality, and how can cities mitigate this? Key takeaways, integration, seamless transfers, e.g., fare integration, shared stations, enhance system efficiency. Sustainability, electrification and TOD reduce urban carbon footprints. Equity, prioritize affordable housing and inclusive design in TOD projects. Future directions, smart transit, AI-driven demand-responsive buses. Microtransit, shuttles feeding into BRT/LRT hubs. This chapter underscores the transformative potential of public transit in creating livable, equitable cities, balancing innovation with inclusivity. Part 3, Traffic Engineering and Management. Chapter 7, Intelligent Transportation Systems, ITS. Intelligent Transportation Systems, ITS, integrate advanced technologies to enhance traffic efficiency, safety, and sustainability. This chapter explores 3 pillars of ITS: adaptive traffic control, connected/autonomous vehicles, and IoT-driven data applications, highlighting their synergies and challenges. 7.1 Traffic Signal Optimization and Adaptive Control Overview. Adaptive traffic control systems dynamically adjust signal timings based on real-time traffic conditions, reducing congestion and emissions. Key technologies: SCOOT, split, cycle, offset optimization technique uses inductive loops to optimize signal phases in cities like London. SCATS, Sydney Coordinated Adaptive Traffic System deployed in Sydney and Los Angeles, adjusts cycle lengths via real-time demand. AI-driven systems, machine learning models predict traffic flow for proactive adjustments, e.g., Pittsburgh SurTrack. Benefits: congestion reduction. Los Angeles saw a 12% drop in travel time after implementation. Emission cuts. Lower idling times reduce CO by 10-20%. Challenges: high initial costs, $50,000, $200,000 per intersection. Integration with legacy infrastructure. Case study: Stockholm's adaptive signals, reduce delays by 30% and emissions by 14% during peak hours. 7.2 Connected and Autonomous Vehicles, CAVs, Overview. CAVs leverage V2V, vehicle-to-vehicle, and V2I, vehicle-to-infrastructure, communication to enhance safety and efficiency. Key concepts: autonomy levels, ranging from level 0, manual, to level 5, full automation. Platooning, truck convoys with synchronized braking, reducing fuel use by 15%, e.g., EU's Ensemble project. Applications: safety, collision avoidance systems in Tesla and Waymo vehicles. Traffic flow, autonomous shuttles in Phoenix's Sun City optimizing last-mile connectivity. Challenges: cybersecurity vulnerabilities, e.g., hacking risks in V2X networks. Ethical dilemmas, e.g., decision-making in unavoidable accidents. Case study: Singapore's autonomous bus trials, reduced peak hour congestion by 20% in Marina Bay. 7.3 Real-time data and IoT applications overview. IoT devices collect and transmit traffic data for real-time monitoring and predictive analytics. Key technologies: sensors, embedded in roads, e.g., Madrid smart pavement for congestion tracking. GPS data, Waze and Google Maps provide crowdsourced traffic updates. Edge computing, local data processing at traffic lights to reduce latency. Applications: dynamic routing, rerouting trucks during accidents via IoT-enabled signage. Predictive maintenance, identifying potholes using vibration sensors in Barcelona. Challenges: data privacy concerns, e.g., tracking individual vehicles. Interoperability between vendors, e.g., Siemens versus Cisco systems. Case study: Dubai's IoT traffic hub integrates 1,000 plus cameras and AI to predict jams with 95% accuracy. Synergies and integration, CAV its coordination, autonomous cars receive signal timings via V2I to optimize speed, e.g., Audi's traffic light information system. IoT enhanced signals, Melbourne uses IoT data to prioritize trams and emergency vehicles. Ethical and environmental considerations, equity, ensuring low-income areas benefit from its investments. Sustainability, life cycle analysis of IoT device production and e-waste. Future trends, 5G enabled IoTs, ultra-low latency for real-time CAV communication. Digital twins, virtual replicas of cities for scenario testing, e.g., Helsinki's 3D traffic model. Discussion questions: 1. Can adaptive traffic systems fully replace fixed-time signals in urban areas? 2. How might CAVs reshape public transit demand and infrastructure? 3. Should governments regulate IoT data ownership to protect privacy? Key takeaways: integration, its success hinges on seamless collaboration between signals, CAVs, and IoT. Equity, policies must ensure marginalized communities access its benefits. Innovation, emerging tech like 5G and AI will drive next-gen traffic solutions. This chapter illustrates how it transforms urban mobility, balancing technological advancement with societal and environmental responsibility. Chapter 8, Safety and Risk Management. This chapter focuses on strategies to enhance road safety through data-driven analysis, infrastructure design, and behavioral insights. It addresses the identification of high-risk areas, protection of vulnerable users, and the role of human behavior in traffic safety. 8.1 Crash Analysis and Black Spot Identification Overview. Black spots are locations with statistically higher crash rates. Identifying and mitigating these areas is critical for reducing traffic fatalities. Methods: data collection, police reports, hospital records, and IoT sensors, e.g., dashcams, GPS. Geospatial analysis, GIS tools, e.g., ArcGIS, map crash clusters and correlate with road features, e.g., sharp curves, poor lighting. Statistical models, empirical Bayes method, combines historical crash data with predictive risk factors. Crash modification factors, CMFs quantify the effectiveness of interventions, e.g., roundabouts reduce crashes by 35%. Case study, London's Black Spot program reduced fatalities by 58% through targeted improvements, e.g., signal upgrades, pedestrian refuges. Solutions: infrastructure, add rumble strips, improve city lines, install LED lighting. Policy: implement Vision Zero initiatives, e.g., Stockholm's 50% fatality reduction since 1997. 8.2 Pedestrian and cyclist safety measures. Key strategies: infrastructure design, protected bike lanes, separated by curbs or bollards, e.g., Copenhagen's 400+ km network. Raised crosswalks, force drivers to slow down, used in Dutch Woonerf zones. Pedestrian hybrid beacons, PHBs, activated by pedestrian push buttons. Technology: LiDAR sensors, detect pedestrians in low visibility, e.g., Volvo's city safety system. Smart crosswalks, illuminate when pedestrians are present, e.g., trials in Seattle. Policy frameworks: complete streets, mandate multimodal road design, adopted in 1,500+ U.S. communities. EU Directive 2019/1936, requires trucks to have improved cyclist visibility. Case study: Amsterdam safety overhaul, cyclist fatalities dropped 70% after expanding protected lanes and traffic calming. 8.3 Human factors and behavioral studies. Behavioral risks: distraction, smartphone use triples crash risk, NHTSA, 2022. Impairment: alcohol contributes to 30% of global traffic deaths, WHO. Speeding: a 5% speed increase raises crash risk by 20%, IIHS. Interventions: education, campaigns like Click It or Ticket, US seatbelt use, 91% in 2023. Enforcement: speed cameras reduce fatalities by 20-25%, OECD. Design: narrow lanes, lower speeds by 5-10 mph, Urban Street Design Guide. Behavioral nudges, optical illusions, e.g., 3D crosswalks, prompt driver caution. Theoretical models: HAD matrix, analyzes pre-crash, crash, and post-crash phases to guide interventions. Theory of planned behavior, predicts compliance with safety laws based on attitudes and norms. Case study: Japan's Shoshin campaign, reduced drunk driving fatalities by 75% through strict penalties and social stigma. Emerging trends: AI-driven risk prediction, machine learning models forecast crash hotspots using weather and traffic data. E-scooter regulation, mandatory helmet laws and geofencing in cities like Paris. Discussion questions: 1. How can cities balance privacy concerns with AI-based crash prediction? 2. Should autonomous vehicles prioritize pedestrian safety over passenger safety in emergencies? 3. Can behavioral nudges replace traditional enforcement measures? Key takeaways: holistic approach, combine engineering, enforcement, and education for maximum impact. Equity, ensure safety measures benefit underserved communities, e.g., school zones in low-income areas. Innovation, leverage technology, e.g., LiDAR, smart crosswalks, to protect vulnerable users. This chapter equips professionals to design safer transportation systems through evidence-based strategies, fostering a culture of safety for all road users. Chapter 9, Freight and Logistics. Freight and logistics form the backbone of global trade, enabling the movement of goods across vast networks. This chapter explores the planning of efficient freight systems, tackles last-mile delivery complexities, and highlights sustainable practices to reduce environmental impacts. 9.1 Freight network planning and intermodal hubs. Key concepts: freight corridors, high-capacity routes, e.g., U.S. Interstate Highway System, EU's TENT core network. Intermodal hubs, facilities where goods transfer between modes, ship, rail, truck, types, ports, e.g., Port of Shanghai, inland terminals, e.g., Duisburg Rail Port, Germany. Design, proximity to highways/rail lines, automated cranes, and digital tracking systems. Optimization tools, GIS routing, minimizes fuel use and delays. Blockchain, enhances transparency in cross-border shipments. Case studies, Port of Rotterdam, automated container handling reduces dwell time by 30%. BNSF Railways Hobart Intermodal Hub, USA links West Coast ports to Midwest markets. Challenges, congestion at major hubs, e.g., Los Angeles/Long Beach ports during COVID-19. Balancing cost and speed in global supply chains. 9.2 Last mile delivery challenges. Key challenges, urban congestion, delivery trucks account for 20% of urban traffic, World Economic Forum. Customer expectations, same-day delivery demands strain logistics. Costs, last mile constitutes 53% of total shipping costs, McKinsey. Innovative solutions, micro-fulfillment centers, small warehouses in urban areas, e.g., Amazon Flex. Autonomous delivery, drones, wing aviation, and robots, Starship Technologies. Crowdsourcing, platforms like Uber Freight for flexible capacity. Case studies, FedEx's Roxo, autonomous delivery robots tested in Dubai and the US, DHL's Cubic cargo bikes reduce emissions in European cities. Emerging trends, AI route optimization, tools like Routeify cut delivery times by 20%. Night deliveries, reduced congestion but face noise restrictions. 9.3 Sustainable freight practices strategies, alternative fuels, electric trucks, Tesla Semi, 500-mile range, Volvo FL Electric. Hydrogen fuel cells, Hyundai Science fleet in Switzerland. Emission reductions, IMO 2020, caps sulfur in marine fuels at 0.5%. Carbon offsets, Maersk's Eco Delivery Program. Circular logistics, reverse logistics, reusable packaging, Loop by TerraCycle. Urban consolidation centers, reduce empty truck miles, e.g., London's Cross River Partnership. Policy and certification, ISO 14001, Environmental Management Standards for Logistics Firms. EU Green Deal, targets 90% emission cuts in transport by 2050. Case studies, IKEA's zero-emission delivery, electric trucks and biofuels in Paris and Shanghai. UPS's Orion system, AI reduces annual mileage by 100 million miles. Challenges, high upfront costs for green technologies. Lack of standardized global regulations. Discussion questions, 1. Can intermodal hubs eliminate bottlenecks in global supply chains? 2. How can cities balance last-mile efficiency with pedestrian safety? 3. Should governments mandate electric freight vehicles, or rely on market incentives? Key takeaways, technology, automation and AI are reshaping freight efficiency. Sustainability, green fuels and circular models are critical for decarbonization. Equity, ensure rural/remote areas benefit from logistics innovations. Future directions, Hyperloop freight, pilot projects in Dubai and Europe. Digital twins, simulate supply chain disruptions, e.g., climate events. This chapter underscores the need for adaptive, sustainable freight systems to meet growing demand while addressing climate and equity challenges. Part 4, Sustainable Transportation Systems. Chapter 10, Green Transportation Infrastructure. This chapter explores strategies to minimize the environmental footprint of transportation systems while enhancing resilience and equity. It focuses on low-impact road design, electric vehicle infrastructure, and pollution mitigation. 10.1 Low-impact development, LID, for roads. Key concepts, permeable pavements, allow stormwater infiltration, reducing runoff, e.g., porous asphalt, pervious concrete. Bioswales and rain gardens, vegetated channels that filter pollutants and recharge groundwater. Green streets, integrate trees, native plants, and natural drainage into urban roads, e.g., Portland's Green Street Program. Benefits: reduces urban heat island effect by 24 degrees C, EPA. Cuts stormwater runoff by 40–80%, protecting aquatic ecosystems. Case studies: Seattle Sea Street, bioswales reduced stormwater volume by 98%. Netherlands climate adaptive roads, solar-powered heated bike paths melt snow, reducing salt use. Challenges: higher upfront costs, 15–25% more than conventional pavements. Maintenance of vegetation and permeable surfaces. 10.2 Electric vehicle, EV, charging networks. Key components: charger types, level 1/2, residential/workplace charging, 322 kW. DC fast chargers, highway corridors, 5350 kW, e.g., Tesla superchargers. Smart grid integration, vehicle-to-grid, V2G, systems balance energy demand, e.g., Nissan Leaf. Deployment strategies: urban hubs, high-density chargers in parking garages and curbsides, e.g., London's ULEV readiness program. Rural equity, federal funding for underserved areas, US NEVI program. Case studies: Norway's EV revolution, 90% of new car sales are EVs, supported by 20,000 public chargers. Electrify America, 800+ stations in the US, powered by 100% renewable energy. Challenges: grid capacity strain during peak demand. Standardization of charging connectors, CCS versus NACS. 10.3 Noise and air pollution mitigation. Noise reduction, acoustic barriers, absorptive materials reduce highway noise by 10–15 dB, e.g., Germany's Larmschutzwande. Low noise pavements, porous asphalt cuts tire noise by 3–5 dB, EU Silent Roads project. Air quality improvements, emission control, electric buses, Shenzhen's all-electric fleet reduces PM 2.5 by 45%. Hydrogen fuel cells, Hyundai's hydrogen trucks in Switzerland eliminate tailpipe emissions. Vegetation buffers, trees along highways absorb CO and particulate matter, e.g., Delhi's vertical gardens. Policy tools, congestion pricing, London's ultra-low emission zone, ULEZ, cut NO by 44%. Euro 7 standards, tighten limits on vehicle particulates and NOx by 2025. Case studies: Singapore's noise regulations, fines for vehicles exceeding 90 dB, paired with quiet pavement trials. California's Advanced Clean Trucks Rule, mandates 60% zero-emission truck sales by 2035. Emerging trends, photocatalytic pavements, TiO-coated surfaces break down NOx pollutants, pilot in Milan. Wireless EV charging, dynamic charging lanes for buses, e.g., Tel Aviv's Electrion. Discussion questions: 1. Can LID techniques offset the environmental costs of road expansion? 2. How can EV charging networks ensure equitable access across socio-economic groups? 3. Should noise pollution be prioritized equally with air quality in urban planning? Key takeaways: integration, pair LID with EV infrastructure for holistic sustainability. Policy synergy, combine emission standards, incentives, and urban design. Community engagement, involve residents in green infrastructure projects to ensure equity. This chapter underscores the transformative potential of green infrastructure in creating cleaner, quieter, and more resilient transportation networks, balancing innovation with inclusivity. Chapter 11, Non-motorized transport. Non-motorized transport, NMT, is central to sustainable urban mobility, promoting health, equity, and environmental benefits. This chapter explores design principles, shared mobility systems, and inclusive urban planning strategies to prioritize walking, cycling, and accessibility. 11.1 Bicycle and pedestrian pathway design. Key principles: safety, protected bike lanes, physically separated from traffic, e.g., Copenhagen's cycle superhighways. Pedestrian refuges, median islands for safe crossing, e.g., Amsterdam's Woonerf zones. Connectivity, continuous networks, seamless routes linking residential areas, transit hubs, and workplaces. Wayfinding, clear signage and apps, e.g., Google Maps bike-friendly routing. Materials, permeable surfaces, reduce flooding, e.g., crushed stone for rural paths. Solar lighting, enhances nighttime safety in low-income areas. Case studies, Bogotá's ciclovia, 550 kilometers of car-free streets on Sundays, used by 2 million people weekly. Tokyo's pedestrian skywalks, elevated pathways reduce congestion in dense districts like Shinjuku. Challenges, retrofitting car-centric cities, e.g., Los Angeles' slow adoption of bike lanes. Balancing space between pedestrians, cyclists, and street vendors. 11.2 Shared mobility, bike sharing and e-scooters systems and trends, bike sharing, docked, station-based systems, e.g., NYC City Bike, 25,000 bikes, 1,500 stations. Dockless, GPS-enabled bikes, e.g., China's OFO, before its collapse. E-scooters, key players, Lime, Bird, and Tyr, e.g., Paris 15,000 e-scooters pre-ban. Regulations, speed limits, 1525 km/h, geofencing, e.g., Barcelona's no-ride zones. Benefits, emission reductions, replaces 30% of car trips under 5 km, ITDP. Equity, subsidized memberships for low-income users, e.g., Chicago's *Divvy for everyone. Challenges, clutter, sidewalk obstruction and vandalism, e.g., San Francisco's 2018 e-scooter ban. Safety, e-scooter injuries rose 222% in the U.S., 2017-2021. Case study, Hangzhou's bike sharing, 86,000 bikes reduced car trips by 8%, but oversupply led to waste. 11.3 Equity and accessibility in urban design. Inclusive design strategies, universal accessibility, ADA compliance, curb ramps, tactile paving, e.g., Japan's Tenji blocks. Low-floor buses, ramps for wheelchairs/strollers, e.g., London's Route Master. Equity-focused planning, priority zones, invest in NMT infrastructure in underserved neighborhoods, e.g., Portland's Green Ring project. Community engagement, CO design with marginalized groups, e.g., Nairobi's Kunkui design initiative. Policy tools, car-free zones, Paris 15-minute city plan prioritizes walkability. Subsidies, Brazil's Bike PE program offers low-interest loans for bicycle purchases. Case studies, Medellin's green corridors, 30 kilometers of shaded walkways/bike lanes in low-income areas reduced heat by 3 degrees Celsius. Barcelona's superblocks, pedestrianized zones cut traffic by 33% and boosted local business revenue. Emerging trends, e-bike incentives, France's €4,000 subsidy for cargo bikes. Smart pedestrian signals, AI detects elderly/disabled users to extend crossing times, trials in Singapore. Discussion questions, 1. Can e-scooters coexist safely with pedestrians in dense cities, or should they be banned? 2. How can cities fund NMT infrastructure without diverting resources from other public services? 3. Should urban design prioritize cultural heritage preservation over modern accessibility needs? Key takeaways, design for all, universal accessibility ensures no one is excluded from mobility. Shared responsibility, public-private partnerships can sustain bike-sharing systems. Climate justice, equitable NMT infrastructure reduces both emissions and social inequality. This chapter highlights the transformative role of non-motorized transport in building healthier, fairer cities, emphasizing design innovation and community-driven solutions. Chapter 12, Climate Resilience. This chapter addresses the urgent need to design transportation systems that withstand climate impacts, reduce carbon footprints, and adapt to escalating extreme weather events. It combines engineering innovation, policy frameworks, and community-driven strategies. 12.1 Flood-resilient infrastructure key strategies: elevated roadways, raise critical routes above floodplains, e.g., Boston's climate-resilient I-90. Permeable pavements, allow water infiltration, e.g., Chicago's Green Alley program. Flood barriers, deployable walls and gates, e.g., Netherlands' Mijslandkering storm surge barrier. Nature-based solutions, wetland restoration, buffer zones absorb floodwaters, e.g., Louisiana's Coastal Master Plan. Bioswales, channel storm water away from roads, Portland's green streets. Case studies: Miami's raising roads, elevated 60-plus roads by 2 feet to combat sea level rise. Japan's underground flood tunnels, Tokyo's metropolitan area outer underground discharge channel diverts 200 tons of water/section. Challenges: high costs, e.g., $2 billion for Miami's road raising project. Balancing flood protection with ecological preservation. 12.2 Carbon-neutral transportation strategies: decarbonization pathways, electrification, EV adoption, Norway's 90% EV market share via tax exemptions and charging incentives. Electric public transit, Shenzhen's 16,000 electric buses eliminate 1.3 m-ton CO/year. Alternative fuels, green hydrogen, Germany's H2BUS initiative for fuel cell buses. Biofuels, Brazil's sugarcane ethanol replaces 40% of gasoline demand. Policy tools, carbon pricing, EU's emissions trading system, ETS, taxes transport emissions. ZEV mandates, California's 2035 ban on gas-powered cars. Case studies: Costa Rica's decarbonization plan, 100% renewable energy for electric trains by 2030. Maersk's methanol-powered ships, first carbon-neutral container vessels by 2024. Challenges: rare earth mineral scarcity for EV batteries. Grid reliability for mass electrification. 12.3 Adaptation to extreme weather events: design innovations, heat-resilient materials, cool pavements, reflective coatings reduce surface temps by 10 degrees Celsius, e.g., Los Angeles Cool Seal. Expansion joints, prevent buckling in railways during heat waves, e.g., Spain's AVE high-speed rail. Storm-resistant infrastructure, wind-resilient bridges, cable-stayed designs, e.g., Hong Kong's Stonecutters Bridge. Submersible roads, Rotterdam's water squares store floodwater during storms. Operational adaptations, predictive analytics, AI weather models, Google's Flood Hub predicts floods 7 days in advance. Real-time monitoring, IoT sensors track road temperatures and cracks, e.g., Arizona. Emergency protocols, evacuation routes, Florida's contraflow lane reversal for hurricanes. Resilient transit, New York MTA's subway sealing program post-Hurricane Sandy. Case studies: Singapore's heat action plan, shaded walkways and cooling bus stops in high-temperature zones. Australia's bushfire-resilient roads, fire-resistant barriers and signage along highways. Emerging trends, self-healing asphalt, microcapsules repair cracks triggered by heat, Dutch trials. Climate-adaptive AI, machine learning optimizes road maintenance schedules based on weather forecasts. Discussion questions: 1. Should flood-prone cities prioritize retreat, relocation, over infrastructure hardening? 2. Can carbon-neutral transport policies exacerbate inequities in developing nations? 3. How can communities balance immediate climate adaptation costs with long-term benefits? Key takeaways: integrated planning, pair flood resilience with green infrastructure, e.g., wetlands and permeable roads. Equity, ensure low-income regions access EV subsidies and cooling infrastructure. Global collaboration, share technologies, e.g., Dutch flood barriers, Nordic EV policies, to accelerate resilience. This chapter equips planners and engineers to future-proof transportation systems against climate threats while advancing equitable, low-carbon mobility. Chapter 13, Autonomous and Connected Vehicles. Autonomous and Connected Vehicles, ACVs, promise to revolutionize transportation by enhancing safety, efficiency, and convenience. This chapter explores the technologies enabling ACVs, ethical dilemmas, regulatory frameworks, and their transformative impact on urban mobility. 13.1 Sensor Technologies and Vehicle-to-Everything, V2X, Communication Sensor Technologies, LiDAR, uses laser pulses for high-resolution 3D mapping, e.g., Waymo's 360 degrees perception system. Radar, detects speed and distance of objects, e.g., Tesla's autopilot. Cameras, vision-based systems for lane detection and traffic sign recognition. Ultrasonic sensors, short-range detection for parking and low-speed maneuvers. V2X communication, V2V, vehicle-to-vehicle collision avoidance via real-time data exchange, e.g., platooning trucks on EU highways. V2I, vehicle-to-infrastructure traffic light coordination, e.g., Audi's traffic light information system. V2N, vehicle-to-network 5G-enabled cloud updates for route optimization. Standards, DSRC, Dedicated Short-Range Communications Legacy US Standard, CV2X, Cellular V2X 5G-backed, supports low-latency communication, adopted in China and EU. Case study, Singapore's V2X pilot, reduced junction waiting times by 25% through smart traffic light syncing. 13.2 Ethical and Regulatory Challenges. Ethical dilemmas, trolley problem, algorithmic decisions in unavoidable accidents, e.g., prioritizing pedestrian versus passenger safety. Bias in AI, training data skews impacting marginalized communities, e.g., poorer recognition of darker skin tones. Regulatory frameworks, US NHTSA guidelines, voluntary safety assessments, e.g., GM Super Cruise. EU's type approval, mandates cybersecurity and data privacy compliance. Global standards, UNIS WP.29 Regulations for Automated Lane-Keeping Systems, ALKS. Key challenges, liability, who is responsible in crashes? E.g., 2018 Uber ATG fatality led to software accountability debates. Data privacy, GPS and biometric data misuse risks, e.g., Tesla's cabin camera controversies. Cybersecurity, vulnerabilities in V2X networks, e.g., GPAC in 2015. 13.3 Impact on urban mobility. Positive impacts, traffic reduction, platooning cuts congestion by 15–25%, OECD. Public transit integration, autonomous shuttles fill first/last mile gaps, e.g., Helsinki's Robobus line. Urban space reclamation, reduced parking needs could repurpose 20% of city land, McKinsey. Risks and challenges, increased VMT, vehicle miles traveled empty AVS circling or induced demand may raise emissions. Equity gaps, high costs could limit access to affluent users, e.g., Waymo's service in Phoenix suburbs. Labor displacement, 3–4 million trucking jobs at risk in the U.S. by 2030, IRU. Case studies, Phoenix, Arizona, Waymo's fully autonomous rideshare serves 1,500 plus square miles, reducing DUI incidents. Oslo, Norway, AV shuttles integrated with public transit apps for seamless multimodal trips. Emerging trends, mobility as a service, MaaS ACVs integrated with apps like Uber and Lyft. Autonomous freight, 2 Simples driverless trucks operating in Arizona Sunbelt corridors. Discussion questions, 1. Should AV algorithms prioritize passenger safety over pedestrians in ethical dilemmas? 2. How can cities ensure equitable access to ACV technologies? 3. Can V2X systems prevent hacking without stifling innovation? Key takeaways, collaboration needed, governments, OEMs, and tech firms must align on safety and equity. Adaptive infrastructure, smart cities must evolve with 5G, dedicated lanes, and updated policies. Sustainability focus, ensure ACVs complement not replace public transit and active mobility. This chapter underscores ACV's potential to redefine mobility, emphasizing balanced innovation that prioritizes safety, equity, and environmental goals. Chapter 14, Smart Cities and Mobility as a Service, MaaS. This chapter explores the integration of technology and urban planning to create efficient, secure, and user-centric transportation systems. It delves into the role of integrated platforms, AI-driven solutions, and blockchain in shaping the future of urban mobility. 14.1 Integrated Mobility Platforms Definition and Functionality. Integrated Mobility Platforms, IMPS, unify diverse transportation modes, public transit, ride-hailing, bike-sharing, and more into a single interface for seamless trip planning, booking, and payment. Examples: WIM, Helsinki offers subscription-based access to trains, buses, taxis, and bikes, reducing car dependency. CityMapper, aggregates real-time data from multiple providers to optimize multimodal routes. Uber and Lyft, partner with public transit agencies to integrate schedules and tickets, e.g., Denver RTD collaboration. Benefits: convenience, single app for end-to-end journeys. Efficiency, reduces congestion by promoting shared and public transit. Sustainability, lowers emissions through optimized routing. Challenges: data sharing, requires collaboration between public/private entities, e.g., GDPR compliance in the EU. Equity, ensuring access for low-income and elderly populations, e.g., Chicago's *Divvy for everyone subsidies. Standardization, adopting formats like GTFS, General Transit Feed Specification, for interoperability. 14.2 AI-driven traffic management applications, adaptive traffic signals. Los Angeles ATSAC, adjusts signals in real time, reducing travel time by 12%. Singapore's Glide, uses AI to prioritize buses and emergency vehicles. Predictive analytics, Google Maps/Waze, leverage machine learning to reroute users around congestion. INRIX, predicts traffic patterns using historical and event data, e.g., sports games. Benefits: congestion reduction, Pittsburgh Surtrack AI cut travel time by 25%. Emission cuts, lower idling decreases CO output by 10–20%. Safety, AI detects accident-prone zones, e.g., NYC's Vision Zero initiative. Challenges: privacy concerns, tracking vehicles via cameras/GPS raises data security issues. Bias risk, algorithms may overlook underserved areas without sufficient data. Infrastructure costs, high initial investment for sensors and AI systems. 14.3 Blockchain for secure transportation networks use cases. Ticketing, Siemens Mobility, blockchain-based tickets prevent fraud in public transit. Sporveien, Oslo pilots blockchain for fare collection. Supply chain transparency, Maersk Tradelands, tracks shipping containers globally, reducing delays and fraud. IBM Food Trust, ensures ethical sourcing in logistics, parallel application. Decentralized ride-sharing, DAV network, peer-to-peer platform for autonomous vehicle transactions. Benefits: security, immutable records prevent tampering, e.g., vehicle maintenance logs. Transparency, real-time tracking of goods/passengers builds trust. Cost savings, reduces intermediaries in payment processing. Challenges: scalability, Bitcoin-like networks struggle with high transaction volumes. Energy consumption, proof-of-work blockchains face sustainability criticism. Regulatory hurdles, lack of global standards for blockchain adoption. Interconnections and synergies, AI and blockchain, secure data sharing for IMPS, e.g., anonymized traffic data stored on blockchain. MaaS ecosystems, AI optimizes routes while blockchain ensures secure payments. Future trends, autonomous integration, IMPs incorporating self-driving cars, e.g., Waymo's Phoenix pilot. Green blockchain, shift to energy-efficient consensus mechanisms, e.g., proof of stake. AI ethics frameworks, developing unbiased algorithms through participatory design. Discussion questions, 1. Can IMPs truly reduce car dependency, or will they inadvertently increase urban sprawl? 2. How can cities balance AI efficiency with privacy rights in traffic management? 3. Is blockchain's energy cost justified by its security benefits in transportation? Conclusion: smart cities must harmonize technology, policy, and equity to build resilient transportation networks. While AI, blockchain, and MOS offer transformative potential, their success hinges on inclusive design, sustainable practices, and cross-sector collaboration. Chapter 15, Advanced Materials and Construction. This chapter explores cutting-edge materials and construction techniques revolutionizing transportation infrastructure, emphasizing sustainability, durability, and innovation. 15.1 Self-healing concrete and smart pavements. Self-healing concrete, mechanism, bacteria-based, Bacillus pseudophirmus spores embedded in concrete activate upon water ingress, producing calcium carbonate to seal cracks. Microcapsules, polymer capsules release healing agents, e.g., epoxy, when cracks form. Benefits: extends lifespan by 20–30%, reducing repair costs. Lowers CO emissions by minimizing frequent maintenance. Case studies: Netherlands self-healing bike path, first application of bacterial concrete in 2016, still intact with minimal repairs. Belgium's Antwerp tunnel, reduced maintenance downtime by 50%. Smart pavements, technologies, piezoelectric materials, generate electricity from traffic vibrations, e.g., Italy's Vibraspeed pilot. Solar roadways, embedded photovoltaic cells, e.g., France's Wattway, though challenged by efficiency and cost. Benefits: energy generation and real-time data collection, e.g., temperature, traffic flow. Enhanced safety with LED-lit road markings. Challenges: high initial costs, e.g., solar roadways cost $2,500/m superscript 2. Long-term durability under heavy traffic. 15.2 3D printing for infrastructure techniques and materials, robotic arm extrusion, MX3DS steel bridge in Amsterdam, printed layer by layer using WAAM, wire arc additive manufacturing. Concrete 3D printing, Kobitz printers used in Germany's 3D printed homes, adaptable for bridges. Polymers and composites, lightweight, corrosion-resistant structures for coastal areas. Benefits: design flexibility, complex geometries, e.g., hollow structures for weight reduction. Waste reduction, precise material use cuts waste by 30–60%. Speed: Dubai's 3D printed office building completed in 17 days. Challenges: material standards, lack of ASTM codes for 3D printed load-bearing structures. Scalability, limited to small/medium projects, e.g., pedestrian bridges. Case studies: MX3D bridge, Amsterdam monitors strain via embedded sensors, demonstrating real-time health analytics. Shanghai's 3D printed bus stop, weather-resistant polymer structure printed in 24 hours. 15.3 Sustainable materials, recycled plastics, bioasphalt, recycled plastics in asphalt, application, India's plastic roads, e.g., China's Jambulingham Street 8–10% plastic waste replaces bitumen, enhancing durability. Benefits: reduces landfill waste, 1 km road consumes 1 million plastic bags. Improves resistance to water damage and rutting. Challenges: microplastic leaching concerns, mitigated by encapsulation techniques. Variable plastic quality affects consistency. Bioasphalt, sources, lignin, byproduct of paper industry, e.g., Netherlands circular bio-based pavement. Microalgae, France's AlgaRoot project produces bio-bitumen from algae oil. Benefits, 50% lower carbon footprint versus conventional asphalt. Renewable and non-toxic. Case study, California's Bioflux pavement, pilot highway section with algae-based binder shows 30% higher elasticity. Standards and certifications, Green Roads trademark, awards points for recycled material use. Cradle to Cradle, C2C certifies sustainable production practices. Comparative analysis, material cost, versus traditional, durability environmental impact self-healing concrete plus 20% high-low, long-term, 3D printed steel plus 15% moderate high-medium, energy-intensive, recycled plastic minus 10% moderate high, waste reduction, bio-asphalt plus 25% moderate low, carbon neutral potential, future trends. Nanotechnology, graphene-enhanced concrete for conductivity and strength. 4D printing, materials that self-assemble or adapt post-construction. Circular economy, closed-loop systems for material reuse in infrastructure. Conclusion, advanced materials and construction methods are pivotal for resilient, sustainable infrastructure. By integrating innovation with environmental stewardship, engineers can address global challenges like climate change and resource scarcity while enhancing urban mobility. Chapter 16, Urban Transportation Innovations. This chapter examines transformative urban transportation projects worldwide, highlighting best practices in cycling infrastructure, rail efficiency, and metro expansion to address congestion, sustainability, and equity. 16.1 Copenhagen cycling infrastructure key features, cycle superhighways, 26 routes, 500 plus km, connecting suburbs to downtown, featuring, priority signals, green wave sync to bike speed, 20 km per hour. Weather adaptations, heated lanes and raised bike paths to prevent snow buildup. Bike-friendly design, cycles lane, bicycle snake elevated bike bridge bypassing pedestrian traffic. Parking hubs, secure facilities at transit stations, e.g., 2,500 space parking at an report station. Impact, modal share, 49% of commutes by bike, 2023, targeting 50% by 2025. CO reduction, avoids 90,000 tons annually. Safety, 70% fewer cyclist fatalities versus 2000. Challenges, costs, $50 m/year for maintenance and expansion. Car integration, reducing car lanes faced initial resistance. Future plans, Green Wave 2.0, AI adjusts signals in real time for e-bike speeds, 25 km per hour. Cargo bike subsidies, replacing 30% of delivery vans by 2030. 16.2 Tokyo's rail network efficiency network overview, scale, 158 lines, 2,200 stations, 5,000 kilometers of track. Operators, JR East, Tokyo Metro, Toei Subway, and private lines. Efficiency drivers, punctuality, 95% on-time rate, delays greater than or equal to 5 minutes require apology certificates. Peak capacity, Shinjuku Station, 3.6 million daily passengers, world's busiest. Passenger pushers, Ashiya manage crowds during rush hours. Technology, automatic train control, ATC, minimizes human error. Energy recapture, regenerative braking saves 20% power. Sustainability, electrification, 100% of commuter rail powered by renewables, 2030 target. Integration, seamless transfers with buses, bikes, and ferries via Suica/Pasmo smart cards. Challenges, aging infrastructure, 30% of stations built pre-1980 require upgrades. Overcrowding, 200% capacity during peaks on Yamanote Line. Innovations, driverless trains, Eurocom Line's fully automated system since 1995. Disaster resilience, earthquake-resistant tracks and floodgates. 16.3 Los Angeles Metro Expansion Project Overview, Purple Line Extension, $9.5 billion subway connecting downtown LA to Westwood, 2027 completion. Regional Connector, Links Blue, Expo, and Gold Lines, 2023, cutting transfer times by 20 minutes. Light Rail, K-Line, Crenshaw/Lax, serves South LA and Lax, 2024. Funding and Policy, Measure M, 1/2 cent sales tax generates $120 billion over 40 years. Equity Focus, Fare Subsidies, low-income fare is $76/year, versus $1,200 standard. Transit-oriented communities, TOC mandates affordable housing near stations. Impact, ridership, 1.2 million daily riders, pre-pandemic, 1.4 m. Emission goals, 25% reduction in transport CO by 2028 Olympics. Challenges, cost overruns, Purple Line tunneling costs rose 40% due to seismic risks. NIMBYism, opposition to density near Beverly Hills stations. Future vision, automated metro lines, Sepulveda Transit Corridor, 2035, with driverless trains. Zero-emission fleet, 100% electric buses by 2030. Comparative analysis, metric Copenhagen Tokyo Los Angeles modal share, public/active, 62%, bike and transit, 80%, rail dominant, 15%, transit, daily ridership 1.4 m, bike trips 40 m, rail passengers 1.2 m, transit riders emission reduction 90,000 tons CO/year 5 m ton CO/year, versus cars, 1.8 m ton CO/year, target, discussion. Questions, 1. Can Copenhagen's cycling model work in car-centric cities like Houston? 2. Should Tokyo prioritize automation over legacy system upgrades? 3. Can LA's metro expansion reverse decades of car dependency? Key takeaways, design for people, Copenhagen prioritizes cyclists, Tokyo centers rail commuters. Equity matters, LA's affordable housing mandates set a global benchmark. Scalability, lessons from these cities can guide megacities in the global south. Conclusion, these case studies demonstrate that innovation, sustained investment, and community-centric design can transform urban mobility even in historically car-dominated cities. Chapter 17, Megaprojects and Lessons Learned. This chapter analyzes 3 landmark transportation megaprojects, highlighting their innovations, challenges, and enduring lessons for future infrastructure development. 17.1 High-speed rail, Shinkansen, Japan, versus TGV, France, Shinkansen, Japan, launch, 1964, Tokyo Olympics, the world's first high-speed rail, HSR, technology, dedicated standard gauge tracks, avoiding shared lines. Earthquake-resistant seismic design and automatic braking systems. Performance, speed, 320 km per hour, current operational max, 99% punctuality rate. Safety, 0 passenger fatalities in 60+ years. Impact, enabled 1-hour commutes between Tokyo and Osaka, 515 kilometers. Catalyzed Japan's post-war economic revival. Challenges, high construction costs, $154/km for Chuo Shinkansen Maglev line. Noise pollution in urban areas. TGV, France, launch, 1981, Paris Lyon, emphasizing speed and integration. Technology, mixed-use tracks, HSR and conventional trains, outside dedicated LGV lines. Record-breaking speed, 574.8 km per hour, 2007 test run. Performance, operational speed, 320 km per hour, connects France to Belgium, Germany, and Spain. Lower construction costs, $20/km versus Shinkansen's $50/km. Impact, reduced air travel between Paris and Marseille, 3h by TGV versus 1 hour 30 minutes flight. Integrated EU rail network via cross-border services. Challenges, profitability issues on less traveled routes. Strikes and labor disputes disrupting service. Lessons learned, Shinkansen, prioritize safety and dedicated infrastructure for reliability. TGV, balance speed with cost efficiency and regional connectivity. 17.2 Panama Canal Expansion Overview, Completion, 2016, adding a third lane for new Panamax ships, 14,000 TEU capacity. Cost, $5.25 billion, 20% over budget. Engineering feats, new locks using 4.4 mm superscript 3 of concrete and water-saving basins. Excavation of 150 m cubic meters of earth. Impact, trade, 6% of global maritime traffic now uses the canal, saving 7,500 kilometers on Asia's east coast routes. Revenue, canal tolls generate $3 billion annually, 10% of Panama's GDP. Challenges, environmental, coral reef damage and freshwater lake depletion. Labor, strikes and disputes delayed construction by 2 years. Lessons learned, risk management, over-budget projects require robust contingency plans. Sustainability, mitigate ecological impacts through adaptive design, e.g., water recycling basins. 17.3 Dubai's autonomous transportation strategy goals, 25% of trips autonomous by 2030. Reduce traffic accidents by 90% and transportation costs by 44%. Key projects, Dubai Metro, driverless since 2009, 90 million annual riders. Autonomous taxis, cruise and Tesla fleets, limited to business districts. Hyperloop, proposed Abu Dhabi-Dubai route, 1,200 km per hour. Progress, 2023 status, 10% autonomous trips, mainly metro and pilot taxis. Challenges, regulatory hurdles for cross-border autonomous testing. Public skepticism about safety. Lessons learned, integration, seamless multimodal systems, e.g., metro and autonomous taxis, enhance adoption. Regulation, proactive policies needed to address liability and cybersecurity. Comparative insights, Project Key Innovation Core Challenge Global Lesson Shinkansen Earthquake Resilience High Capital Costs Dedicated Infrastructure Pays Off TGV Cross-Border Interoperability Profitability on Rural Routes Balance Speed with Affordability Panama Canal Water Saving Lock Design Environmental Degradation. Prioritize Eco-Engineering Dubai Strategy Multimodal Autonomy Integration Public Trust in AI Systems Regulatory Frameworks are key conclusion. Megaprojects demand visionary planning, adaptive risk management, and stakeholder collaboration. By learning from past triumphs and failures, future projects can better balance ambition with sustainability and equity. Appendices A conversion tables and engineering formulas. Key conversions, parameter conversion 1 mile, mi, equals 1.609 kilometers, km, 1 kilometer, km, equals 0.621 miles, mi, 1 foot, foot, equals 0.3048 meters, m, 1 pound per square inch, psi, equals 6.895 kilopascals, kPa, 1 mile per hour equals 1.609 kilometers per hour. Ashto Green Book formulas, 1 stopping sight distance, SSD equals 1.47 v plus frac v230 f pmg v design speed mph t reaction time 2.5 sec f coefficient of friction G_grade, decimal, 2. Pavement design, Ashto 1993 /log_10, W_18, equals Z_R_R/S_0 plus 9.36 /log_10, SN plus 1, 0.20 plus /frac /log_10, /delta psi/4.2, 0.40 plus, 1094 SN plus 1, 5.19, W_18 traffic load, ESALs, SN structural number 3. Traffic flow, green shields model /Q equals K /dot V equals K /dot, V_F /dot, 1, /frac KK _J, Q /flow, V/HR, K /density, V/km, V_F free flow speed -B sample designs 1. Signalized intersection, 4-legged, lane configuration, 2 through lanes plus 1 left turn lane per approach. Pedestrian crosswalks with countdown timers. Signal timing, cycle length, 90 SEC, peak, 120 SEC, off-peak. Yellow/all red intervals, 3.5 SEC/2.0 Sector 2. Flexible pavement, urban arterial, layers, surface, 100 mm HMA, PG 64-22 binder. Base, 200 mm crushed aggregate, Ashto number 57. Subbase, 150 mm granular fill, CBR greater than or equal to 20. 3F charging station layout, components, 4 DC fast chargers, 150 kilowatts, 10 level 2 chargers, 7.4 kilowatts. Solar canopy, 100 kilowatts capacity, with battery storage. Spacing, 3.5 m between stalls for accessibility. -C regulatory checklists 1. Safety compliance checklist, guardrails installed on embankments 1.5 m, retroreflective signage, MUCT standards. ADA compliant ramps at crosswalks. Emergency pull-off areas every 1.5 km on highways. 2 environmental compliance checklist, stormwater management plan, EPA NPDES. Noise barriers 6 dBA reduction, FHWA Tiger. Endangered species habitat assessment, ESA Section 7. Construction waste recycled, greater than or equal to 75% per lead. -D Glossary of Transportation Terminology, AADT, Annual Average Daily Traffic. LOS, Level of Service, AF Grading. V2X, Vehicle to Everything Communication. HOV, High Occupancy Vehicle Lane. RUC, Road User Charging. TOD, Transit Oriented Development. References Peer Review Journals 1. Transportation Research Part A, Policy and Practice, Impact of Congestion Pricing on Urban Equity, a case study of London's 10.1016/J.Tra.2023.103456. 2 Journal of Transportation Engineering, Self-Healing Concrete, A Decade of Innovation. doi, 10.1061/ASCE, TE.1943-5436.0000987. ULEZ. doi, Industry Standards 1. Ashto, A Policy on Geometric Design of Highways and Streets, Green Book, 8th edition, 2024. 2 FHWA, Manual on Uniform Traffic Control Devices, MUCT, 11th edition, 2023. 3 IT, Traffic Engineering Handbook, 7th edition, 2022. Textbooks 1. Garber, N., and Hole, L., 2024. Traffic and Highway Engineering, 7th edition. Cengage Learning. ISBN 978-1337-55803-9. 2 Meyer, M., and Miller, E., 2023. Urban Transportation Planning, 3rd edition. McGraw-Hill. ISBN, 978-1-2604563-8. Online resources, Federal Highway Administration, FHWA www.fwa.dot.gov, https://www.fwa.gov, Transportation Research Board, TRB www.trb.org, https://www.trb.org. Note, appendices and references are designed for quick lookup and compliance verification. For detailed calculations or regulatory updates, consult the cited sources or relevant authorities. Let me know if you need further refinements.